So last time we updated our understanding of electric force on two charges, right? In grade 11, we defined force on a charge as the force a charge experiences when it's inside some external electric field. This year we talked about, well, we can actually figure out what force one charge exerts on another because of the field that it's creating, right? And now we're going to update our understanding of electric fields as well for point charges. So let's first of all just draw some fields around each of these things to remind ourselves what they look like. So these are all separate. They're not anywhere near each other. It's just for the sake of space on the page, that's why they're so close to each other. So we remember that an electric field points in the direction of the force on a positive charge, right? So this positive charge over here will push away other positive charges, and so the field it creates looks something like that. Now we could draw an unlimited number of field lines, but what we really want to do is give an idea of the shape of the field. So that'll do just fine. That also means that a negative charge, like the one on the right, will pull positive charges into it. And so the field that it creates will have the same shape, it'll just have the opposite direction compared to the other one. Now the tricky one is the one in the middle here. The field around both of these things is going to be a combination of those two things happening, right? So the positive charge over here wants to push away other positive charges, and the negative charge wants to attract positive charges, and then in the middle we will have a combination of those two things happening. So it ends up looking like this. What a beautiful pattern. Now I'm not going to complete all of it. This will do just fine. There you go. So there's what those fields look like again. Now when we're calculating the strength of an electric field, we're figuring out what force does it experience and how much charge does it have. The electric field strength is the force per unit of charge that this charge experiences. So now we can update our definition of an electric field, or of electric field strength, using Coulomb's law, which is this thing over here, which we learned last time, and last year's version of electric force, which is right over there. So Coulomb's law doesn't have electric field in the formula anywhere, right? So we can't just use that, but when a charge is experiencing a force due to an electric field because of some other charge, we can say that those two versions of the formula are equal to each other. Okay, and so here's what we get when we set one of them equal to the other. K Q1 Q2 over R squared, that's one version of electric force, that's equal to Q1 E. Okay, usually we just did force equals QE because we weren't necessarily talking about two different charges, we were just talking about one charge last year. But now, because we are talking about one charge being affected by another charge, then we have to label them number 1 and number 2. So in this case, number 1 is experiencing the force. That's our subject. So we have a Q1 on both sides of the equation here, and so they can both get canceled out. And that gives us our final equation for electric field strength. We get E is equal to KQ2 over R squared. I'm not going to put the 2 in for the Q2. The understanding here is that this Q here, this Q is the Q that is creating the field. Okay? And the K value is Coulomb's constant, which is 9 times 10 to the 9, as long as you're working in coulombs. And the R value is the distance between the originating charge and the charge that's experiencing the force. Okay, so now we've got a new updated version of our electric field formula. So let's try a couple examples here. At point A, there is a charge of 1.6 microcoulombs. Here, let's just right away remember that micro is times 10 to the negative 6. And at point B, which is 60 centimeters to the right of point A, 60 centimeters, not really the unit we want either, so that would be 0.6 meters. There is a charge of negative 0.4 microcoulombs. That's also going to be times 10 to the negative 6. So here's the situation. We've got a positive charge right over there. That's point A. And at point B, which is 60 centimeters to the right, it's right over here, we have a negative point charge, so that's point B. Now we have to remember that this positive charge at point A is making a field that looks like this. Right? It's pointing away. Now I don't really need a full field over here, but the point is that the charge at point B is experiencing a field in that direction. Okay, that's the field that it's experiencing. It's a negative charge experiencing a field in that direction. So we are trying to figure out, first of all, what is the electric field at that point. So the field is being made by point A, being made by charge A, and so when we do E equals KQ over R squared, we want to use QA there because it's the one that's creating the field. So then we're going to put in our units over here. This is a vector quantity, so we really should put the arrows on top. That gives us 9 times 10 to the 9 times the charge, which is 1.6 times 10 to the negative 6 coulombs. And the distance we're talking about is 0.6 meters. Okay, now let me fix this for a second here. That shouldn't have been R2, should have been R squared. And that means that we're taking this right over here and squaring it. And so the quantity that we get then for the field strength is 40,000 newtons per coulomb. Okay, but there should be a direction on that. The question really isn't asking you for the direction necessarily. What's the direction of the electric field there? It's just asking you for the strength, because the question really, I mean, I guess it doesn't really tell you what direction it is, but you should know, right? So because of A is creating a field that at that point would be pointed toward the right. Okay, now let's figure out the force on the charge at B. So we could use Coulomb's law, which would be K Q1 Q2 over R squared. That would be totally fine because we have both charges and we have the distance between them and we have the K value, so we could figure out what the force is. But in this case, because we know the field strength that B is experiencing, we can just use the simpler version of this thing. Fe equals QB times E. Right? So that's the version that we learned last year. So the electric force that it's going to experience will be its charge, which was 1.6 times 10. Let me try that again. I think it's actually 0.4, isn't it? Yes, it is. It's 0.4 times 10 to the negative 6 coulombs times the field that it's experiencing, which is 40,000 newtons per coulomb. Now this is a negative charge. I'm not putting the polarity in this equation here because I would prefer to logic out what direction things are happening in. Okay, it does work to put the directions in here because this 40,000 newtons per coulomb, that's to the right, and that's the force, or that would be the direction of the force on a positive charge. This is a negative charge, and so it's going to experience the opposite force. It's going to experience a force to the left. This gives us 0.016 newtons, and that would be to the left. Okay, because again, a negative charge will experience a force in a direction that's opposite the field direction. Let's try the second one. Two equal charges, A and B, of 0.6 microcoulombs are separated by 60 centimeters. Consider a third location, C, that is 60 centimeters from both of the charges. what is the net electric field at location C? Okay, so I've drawn this out for you already here. The only way that this actually works is if it's an equilateral triangle, and so that's what we have. So we're trying to figure out what is the field strength at C. Not just the strength, but also the direction at C. Okay, so C is going to be experiencing a field. One moment. C is going to be experiencing a field from B pointing this direction. Oh boy, let's try that again. Pointing this direction, sure. And C is going to be experiencing a field pointing this direction from A, because A and B are both positive charges. And so that's what I've got drawn below there. We've got point C is experiencing two different fields. Now, our job here is to figure out what's the total. What's the net electric field at C? So we have to add those two things up. But here's the thing. Because they are at different angles, we have to add them up using components. So I need to know that that angle is 60 degrees. It doesn't tell me in the question, but because this is an equilateral triangle, we know all three angles have to be equal to each other. They all have to be 60 degrees because they have to add up to 180. That's a little fact that maybe is in the back of your brain somewhere, but it's necessary for this thing. So we've got two fields that are adding up at C. We've got an X component and a Y component for both of them, right? And we've got 60 degrees here and 60 degrees here. Now, I can see already that my two X components here, they are equal to one another, but in opposite directions. So they're going to cancel each other out. My two Y components are also equal to one another, but they are in the same direction. So what I'm going to end up doing in this question is just figuring out what are the Y components and then adding them up. Two Y components. Okay? So this is going to end up being a pretty simple question in the end because of how symmetrical everything is. So let's try this out. So with the field, because of A at C is equal to KQA over R squared, which is 9 times 10 to the 9 times 0.6 times 10 to the negative 6 coulombs divided by the R is 0.6 meters, and we're going to square that. And what we get for that value is 15,000 newtons per coulomb. Okay, now that is also going to be equal to the field because of B at location C, right? They're going to be the same as one another. But those are both at an angle. So we need to figure out what is the Y component of that thing. So the Y component is going to be the sine, right? Because it's the opposite side. And so we want the total field, E net, is going to be just 2 times the Y component, which is 2 times 15,000 newtons per coulomb times the sine of 60 degrees. Right? That'll get us the Y component of that thing. And so in the end, we get an answer of 2.6 times 10 to the 4 newtons per coulomb. And those things both point north. And there's our final answer. Let's try a more complex example. A 5 microcoulomb charge, charge A, is 40 centimeters to the left of a 4 microcoulomb charge, which we'll call charge B. There is a location somewhere between the two where those two fields cancel each other out. And we're looking for where is that point. How far is it from A? How far is it from B? Okay, that's the goal. So I've drawn the situation over here for us to get a sense of what's going on and what we're looking for. And hopefully that will lead us to how we would set this thing up. So we've got two charges. The total distance between them is 0.4 meters. I've just changed the 40 centimeters into meters, which we need anyway. And then we're looking for a point that is some distance from A and some distance from B. So that distance usually in our electric field formula is labeled R, lowercase r. In this case, we can't use just that because we'll get two different answers for it, right? So I've just named one of them big R and one of them little r. Same thing, it's just that big R is the distance from A and little r is the distance from B. I did that because charge A is stronger than charge B, right? And so that 0 point is probably going to be closer to B than it is to A. So here's how we're going to set this thing up. We know that at that point, the total electric field is 0. And what that means is that the field because of A is the same strength as the field because of B, right? We know that since they're both positive charges, they're going to point away from themselves, right? And so what we're looking for is, where is the strength of A the same as the strength of B, because their directions will cause it to cancel out at that point. Okay? So, here's how I'm going to set this up. We're just going to start with the field because of A at this point that we're talking about is equal to the field because of B. Now, I'm not going to make either of these vectors because really what I'm just looking for is where the magnitude is the same. I know that the directions are the opposite direction. I know that the directions are the opposite direction. And so all I really need to know is where are the magnitudes the same. So we have a formula for each of these things. That's KQA over big R squared, right? And then KQB over little r squared. Two different r's, okay? Because they're not going to be the same value that we're searching for. Okay, so I can fill in my k values and my charges, but I can't fill in either r value, right? I can't fill in either r value because I don't know either of them. But they are related to each other, right? I know that the total distance in between those two charges is 0.4 meters. And so let's just say that big R is 0.4 meters minus little r. Does that make sense? The total distance is 0.4 meters. If I subtract little r from that, I get big R. So here's what we're going to do. We're going to replace that big R with 0.4 minus little r. So it goes like this now. KQA over 0.4 minus little r squared is equal to KQB over little r squared. Okay, so now we don't have two unknowns in our formula. Now we just have one unknown, but it's in two places. And that's where the complexity of this one comes in. Whenever we have one variable in multiple places in an equation, then we need to collect those variables. We need to put them in the same spot and combine them somehow so that when we are solving for it, we are only solving in that one spot. Has to work that way. So now the rest of our job here is to find out how to collect that r in one spot. So we're just going to use our algebra skills here to try to simplify this as much as we can. The first thing that I can do is cancel out these k's. Right? There's a k on both sides, both on the top of the equation, so I can just get rid of it. Divide both sides by k, done. So I've simplified it already. Now, the second thing that I'm going to do is I'm going to cross multiply, let's just call it that, so that this isn't two fractions anymore. Now I just want a straight line equation. So I need to multiply the right side by 0.4 minus r squared, and I need to multiply the left side by r squared. And here's what that gets me. Now we're getting longer. QA times r squared equals QB times 0.4 minus r also squared. Okay. This looks simpler. Maybe this looks doable. So I have an r within the brackets over here, and that thing is giving me trouble. So I want to get rid of the brackets, because again, my goal is to collect the r's in the same spot. so that I can combine them. But the 0.4 minus r within the brackets is squared, so I need to do a binomial expansion here. Oh, we're getting into quadratics, friends. I need to do a binomial expansion, which means I'm doing 0.4 minus r times 0.4 minus r. And you've got to FOIL it. Oh, hopefully all of that is ringing such loud bells in your head. QA r squared is equal to QB times, here we go, 0.16. That's 0.4 times 0.4, that's that part, minus 0.8 r plus r squared. That's a quadratic. This is going to be fun. Okay, so now I want to distribute the QB into the brackets over here so I can completely get rid of those brackets. So I have QA r squared equals QB times, I'm going to put the r squared term in the front. QB times negative 0.8r is negative QB times 0.8r. And then the last one, plus QB times 0.16. Next, to make this something that's a bit more recognizable to you, we're going to move the QA and the r squared to the right side of the equation. Okay, so because this is an r squared term, and we've already got a QB r squared term over here, we can combine those two terms. So here we go. On the left, we've got 0 equals. And then when I do QB r squared minus QA r squared, I get QB minus QA, all of that times r squared, minus QB, all the other stuff that we had here. That's an r. Okay. Now I'm going to put in all of my Q's, because remember, I actually have all of that information. I'm told that charge A is positive 5 microcoulombs, and charge B is positive 4 microcoulombs. So all these Q's that are in here, they aren't actually variables, they're actually real numbers. So I can put those things in here. I'm going to combine them at the same time though, okay? So we get 0 equals QB minus QA is negative 1 times 10 to the negative 6. That's that thing, times r squared. Minus, then we're going to do QB times 0.8, which gives us negative 3.2 times 10 to the negative 6r. And then we're going to do QB times 0.16 and just put those both together right away. So we get plus 6.4 times 10 to the negative 7. Okay, now you might recognize this as a quadratic function, right? Because we've got an r squared term, or think of it as an x squared term. We've got an r term, our x term, and we've got our constant term over here. Okay, and so to solve for r, we need to use the quadratic formula. Yes, we have to use the quadratic formula. Now, to be honest, this is not going to be the type of question that's super common in our practice on tests or anything like that. This is a real challenge question. So here's our quadratic formula, in case you don't remember it. It is on your formula sheet, I think. Negative b plus or minus the square root of b squared minus 4ac, and this whole thing is over 2a. Now, we should make sure that we label these things so that they're all understandable. That's our a value. This is our b value. This is our c value. And so we're just going to insert those things into our quadratic formula. So bear with me while I do that. I'm going to do it a little quickly. And once you put all of that together, you get an r value. And remember, this is little r is the distance from charge B to our 0 point, our point where the fields cancel each other out. So we get two answers, right? As you'll get for any time you use the quadratic function because of this plus or minus over here, right? The plus or minus gives you two answers, and you're just going to have to figure out which one actually makes sense for this situation. So you can either get negative 3.39 meters or 0.189 meters. Okay? I think that it should be fairly obvious which one is the correct one here. It would not make sense for a value of negative 3.39 meters, right? Because we're looking for what's the distance from B toward A in order to figure out that 0 point. And there is only 0.4 meters between the two charges, right? So we couldn't have 3.39 meters of any sort there. And so our answer has to be 0.189 meters. And if that is the case, that means that our distance from A is going to be whatever the difference is. Okay, so big R would be 0.4 minus 0.189, and so we get 0.211 meters. That is from charge A. So there are two answers. We are 0.189 meters from charge B, and we are 0.211 meters from charge A, and that follows what we expected.